All right, we ended the class on Tuesday with talking about weak acids, weak bases, strong acids, and strong bases. And these were the four that we've done. So if you want to kind of go back to them, we're going to talk just a little bit about each one of these a bit more. And in dealing with them a bit more, let's just review a couple things. First of all, when we look at these equations, if I didn't have these labeled here, how do we know which ones is a base? What would we look at? OH negative, exactly. It's going to have the hydroxide ion. And if it's an acid, what do we look for? H3O plus, exactly. So here's our acids, the ones that I've put in red, and then the part that identifies it as a base we put in blue. What does the double arrow stand for in these cases? No, they're reversible. They're ones that, and specifically, what types of acids or bases do we use them for? Weak ones, right. We have the weak base here, the weak acid there. And what that tells us is that there's not a lot of product, there's not a lot of ions in the solution. And what was the evidence that we had when we did the demos that showed us there was little ions or few ions in solution? Right, we had the dim light. So the weak base, the weak acid had the dim lights when we put them in solution. The strong acid, strong base had the brighter lights. Now, the other thing we're noticing is that this last one is written just a tad differently. And in this last one, we've not written it as a reaction with water. And the reason for that is because sodium hydroxide is an ionic compound already. And because it is an ionic compound, it simply goes through the process of dissociation. Now, dissociation isn't necessarily a scientific word. It's a word that's not necessarily in everyday's vocabulary either, but what does it mean if we dissociate something? It means we take it apart, exactly. So if we dissociate yourself with something, maybe it's a Facebook friend or something because you don't like what they have to say about politics, you've gone through dissociation. In this case here, when we talk about dissociation, what it means is that when we place the sodium hydroxide in water, the ions dissociate from each other and form those ions in solution that conduct electricity. These first, let's see, color, how about a black one here? These first three represent the process of ionization. And we talk about ionizing something, and this is a term from very, very early on in the semester. If we ionize something, that means that we're making ions out of something that wasn't ionic to begin with. So these are molecular compounds, and what happens when these molecular compounds are put together, they go through a reaction and they form ions. And so that's what it means when we talk about ionization. We don't talk about ionization occurring for this one because it already is an ionic compound. In this case, the ions simply dissociate when we place it into water. So, that said, one of the things we did not get to on Tuesday was how we lump together a larger category of acids and bases. Now, don't write all these down. I mean, for one thing, it'll be all the notes are there, but listen carefully here, kind of how this will help keep things straight for you. First of all, if I'm going to learn something, or suggest to you to learn something about these, what I would learn is the strong acids and the strong bases. Because if you learn these, this is a complete list of strong acids. If you learn this complete list of strong acids, then all other acids you encounter will be classified as weak acids. If you learn these strong bases, then any other base that you encounter is going to be a weak base. So if you're going to concentrate on learning anything, learn your strong acids and your strong bases, because these are complete lists, and anything besides them, any other acid is going to be a weak acid, any other base is going to be a strong, any other base is going to be a weak base. Now, The most common weak acids we encounter will be these. Most common weak base we would encounter would be ammonia. So these are the most common, but again, the list of weak acids would just go through the floor. The list of weak bases would go through the floor because there's so many weak acids and weak bases we can't list what they all are. But again, the ones that I listed here are some common ones that are going to show up in your homework and so forth. Now on the strong bases, when we talk about group 1A and group 2A hydroxides, what does the group 1A and group 2A mean or refer to? Sooner we answer questions, sooner we get out of here today. On the periodic table, right. So if we look on our periodic table right here, group 1A and group 2A, these are the ones that when they form hydroxides are going to be your strong acids and, your strong bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and then from calcium hydroxide on down. We do not include beryllium and magnesium hydroxide in this list. So otherwise, all the group 1A and group 2A hydroxides. And then again, on the weak bases, any other hydroxide you run into or carbonates that you run into would be on the weak base list. And again, there's many, 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 many more on each one of these on the weak side. So that said, any questions on these? See how well you understand this. And by the way, this is not a trick question. You may think that it appears in a couple different places on that list. Not intended to be that. If you know the name of that substance, you know which category it belongs to. So is this substance a strong acid, a weak acid, strong base, or weak base? And we'll count down. 5, 4, 3, 2, 1. And here's a weak acid. Weak acid because it's, first of all, it's an acid. How do we know by looking at this that it is an acid?
The H2.
The H2, the hydrogen in the front of the formula. If we see a hydrogen in the front of the formula, it tells us it's an acid, so that rules out these two right away. Then we have to tell whether it's a strong acid or weak acid. And remember, this is a complete list of strong acids. So if we don't see the acid on this list, that must mean that it is a weak acid. That's the only other option that we could have. All right, next 3 questions. They're not things that we've covered yet, but things that you've probably heard in the past. And so I want to see what you already know about pH. The next 3 are about the pH scale. So which of the following pH values is or are neutral? 5, 4, 3, 2, 1. And we're going to come back to that one. So let's do this one. Which of these pH values would be acidic? And select all that apply. 5, 4, 3, 2, 1. And then on the next one, which of these pH values would be basic? And select all of the possible answers. 5, 4, 3, 2, 1. And let's do a quick check here. We'll go back to this one, and we'll see pH of 7. So now, whether you got this right or not, let's go ahead and start writing down some of this information. We have a pH scale, and on that pH scale, neutral sits right here in the middle, and neutral is a pH of 7. On the basic side and the acidic side, let's see what we came up with on our next answers. So this one here we wanted to see. Very good. 1 and 4 are the acidic pHs. So anything less than the pH of 7 is going to be acidic. And so anything in this range, the 0 to 7, is in the acid range, which means that anything between 7 and 14 is going to be in the basic range. And let's see how we did on that next one. All right. So kind of mirrored the other one. Well then, what we need to do, and then one more impression question. And the impression question is this one. Let's see what you know about pHs. You have an acidic solution that has a pH of 3, and we compare it to one that has a pH of 6. I'd like to know how acidic is the one at a pH of 3 compared to the one at a pH of 6. 5, 4, 3, 2, 1. The answer is 1,000 times more acidic. Now, that's one of the huge problems that the general public has when it looks at something like pH. And the reason for that is the pH is based on a logarithmic scale. And if you use logarithmic scale and the word logarithm scares you, don't worry about that. We're going to teach you about logarithms here in just a moment. But the general public doesn't know or understand logarithms. But they come into play here, and they come into play a few other places. And so when we talk about the pH, here's how the pH is defined. In mathematics, the letter P stands for the negative logarithm of. And so specifically, when we talk about the pH here stands for the power of hydrogen. Stands for the power of hydrogen. And again, P stands for taking the negative logarithm of a quantity. In this case, we're going to take the negative logarithm of the hydrogen ion concentration. And when we look at this equation here, when you see the square brackets stand for molarity. So when we place quantities, when chemists place quantities in square brackets, what we're telling you is this: we should place the molarity into those brackets. Now, a couple things. First of all, let's talk about what the logarithm is or does and why it's called the power of hydrogen. Works something like this. Let's say that we want to take the logarithm of 10 to the 12th. Now, I know some people have had this already in here. What is the logarithm of 10 to the 12th?
12.
12, right. And what is the logarithm of 10 to the negative 8th? Negative 8. So that means the logarithm of 10 to the x is equal to x, right. So see, we've covered here in about 30 seconds what takes about a whole class period in math to do. And this is logarithms, and that's how they work. Okay? Now, the other thing that we need to talk about is this hydrogen ion. Now, this hydrogen ion is kind of a weird guy. We're going to start talking about it by looking first at the hydrogen atom. And this is the most theory we're going to have here today, is what we're doing here the next about 3 or 4 minutes. Okay, the rest is going to be math, but this is our theory. So let's first look at a hydrogen atom. And it'll take us back to where we were at the beginning of the semester. If we want to talk about the construction of a hydrogen atom, how many protons are in its nucleus? How many? 1. And where does that come from? Atomic number. So there's 1 proton in its nucleus. And surrounding that 1 proton is how many electrons? Just 1. And where does that number come from? Comes from its atomic number. As long as we have a neutral atom, the number of protons and electrons are equal. But now, let's change this from a hydrogen atom to a hydrogen ion. If we change this to a hydrogen ion, what does a plus charge mean has happened here? It means that we lost an electron. And if we lose this electron, what does that mean we have left? It means we just have left a proton. And so it turns out that a hydrogen ion and a proton are the same thing. And a hydrogen ion or proton represents the same thing. Now, here's the problem, though, with the proton. A proton is super concentrated in charge. Because if we think now about the atom, we talked about it before, we said that if we can take the nucleus and blow it up to the size of a housefly, then we wind up increasing the size of the atom to the size of a large stadium. And so there's a huge difference. So if we strip that electron out, which would take up that size of the whole stadium, we're left behind with that housefly size thing, or in this case, the proton, which is very, very, very tiny, but it still has that positive charge. And so because its charge is so concentrated, that means it has to seek out something else. It doesn't mean that it has to. It means it's going to seek out anything else that has a negative charge, because opposites will attract each other. And so what it winds up seeking out is this. It winds out seeking out another molecule of water. And a molecule of water, we write something along the lines of this right here. And what will happen then is that this proton is very much attracted to those lone pairs on this water molecule. And so once it attracts itself, then what happens is it winds up attaching to that water molecule and makes something like this. And of course, we have a leftover positive charge. And of course, this particle again is called hydronium ion. Exactly. So what happens then is that a proton or hydrogen ion attaches itself to a water molecule and forms a hydronium ion. And so today, when we write out the equation for finding the pH, we actually write it like this. We write the pH as the negative logarithm of the hydronium ion concentration. And the reason why we write it like this today, and here's the original definition, and here's how we write it today. The reason why we write it as hydronium ions is because, again, we really can't have protons by themselves in solution. Because protons are so concentrated in charge, if there's ever one that forms, it'll immediately attach itself onto molecules of water. And so we still call it the pH, though, that we don't call it like the power of hydronium. But this here then winds up being one of those three equations we talked about the other day that we need to memorize. And that is the pH, memorize, or I guess I'm going to provide it on your equation sheet. But it's one here that we're going to be using here at the end of the hour today. Okay, any questions with that?
I have a question.
Yes, go ahead.
Since we said that oxygen can only form two bonds, how does the hydronium ion work?
Okay, well, when we say that it forms two bonds, I can't say I was really lying to you at the time, but in a way, maybe I was. That's when we're talking about neutral atoms. As soon as you start forming polyatomic ions, those rules we talked about can all be thrown out the window.
Oh, okay.
Because in this case here now, this proton is coming with no electrons attaching to it, so it's basically being attracted to whatever electrons are out there on that oxygen. And you'll see that when we talk about oxygen always forming two bonds, well, that always is for intro-level classes, okay? It turns out that in the real world, it can form more bonds, sometimes less. Its most common number of bonds, though, by far is two bonds. But here's one case, and there's always, they're not even called exceptions. When we look at polyatomic ions, then it's always going to be something different. So when we talked about this number of bonds, we're always looking at neutral atoms. Okay, any others? Okay, next up then is what we call the self-ionization of water. Now, in the self-ionization of water, we look at a reaction that goes something like this. We take two molecules of water and we react them together. When they react together, they form hydronium ions and hydroxide ions. That's called the self-ionization of water. That means that water by itself will form ions. But now, if I went and took some water, like we demonstrated the other day, if I took some water out of here, some deionized water, and we checked to see whether or not it conducted electricity, what did we find? It doesn't conduct. And it doesn't conduct because the number of ions in solution are going to be very, very, very small. If there was a lot of ions in solution, we would have seen the light bulb light up, but we didn't, so that tells us that these concentrations are small. But they are measurable, and chemists have measured them. Turns out that the concentration of each one of these is 10 to the negative 7th molar at 25 degrees Celsius. So again, their concentrations, 10 to the negative 7th molar at 25 degrees Celsius. And that's not only for the hydronium ion, I'll put them down here for each one, that's for the hydroxide ion as well. Again, these are at 25 degrees Celsius. So, what we'd like to do next then is this. We'd like to calculate the pH of pure water at 25 degrees Celsius. We go back to our formula, which tells us the pH is equal to the negative logarithm of the hydronium ion concentration. Then we come back here and we say, well, what is that concentration of hydronium ions? And we see that concentration is 10 to the negative 7th molar. So we're going to take the negative logarithm of 10 to the negative 7th. Well, now we're logarithm experts. The logarithm of 10 to the negative 7th is?
Negative 7.
Negative 7. But that sign in front of it there tells us we need to change the sign. We want to take the opposite of negative 7, and the opposite of negative 7 is 7. So if you're wondering where a pH of 7 comes from and why we say that's a neutral solution, here's exactly why it's a neutral solution. It's because of the fact that the hydronium ion concentration in pure water is 10 to the negative 7th molar. If we want to calculate another value, there's another value called the pOH. Now, if the pH is the power of hydrogen, that must mean that the pOH is the power of hydroxide. And the way that we calculate the pOH, remember P again means to take the negative log of the quantity. So we're going to take the negative logarithm of the hydroxide ion concentration. And so we want to calculate the pOH of pure water at 25 degrees Celsius. Well, we've just done this math right here because remember that the hydroxide ion concentration is the same as the hydronium ion concentration. So we plug in 10 to the negative 7th for its concentration. The logarithm of 10 to the negative 7 is negative 7. We then want to take the opposite of negative 7, which is going to give us a value of 7. Which leads us to the third and last equation we'll be using today, which looks like this. Tells us that the sum of the pH and the pOH will always sum to be 14.00 at a temperature of 25 degrees Celsius. And so the three equations that you'll be working with on your homework and that you'll be expected to use on your exam next week will be these three right here. So it's the formula for the pH, the formula for the pOH, and then the sum of the pH and pOH summing to yield 14.00. Let's say if the hydronium ion concentration is equal to 10 to the negative 4th molar, we'd like to know what is the pH and the pOH. And these are the next two questions on the Socrative app. If the hydronium ion concentration is 10 to the negative fourth molar, what is the pH and the pOH? 5, 4, 3, 2, 1. pH is 4. It's a positive 4. Which means then, if we go to the next one, we want to know the pOH. We'll go 5, 4, 3, 2, 1. Answer on this is going to be 10. Okay, it's going to be 10. Now, the reason for that, we come back here and see how these are calculated. Remember that the pH is equal to the negative logarithm of the hydronium ion concentration. And most of us, almost all of us, got this one right, which means we're going to take the negative logarithm of 10 to the negative fourth. Log of 10 to the negative fourth is negative 4. We then take the opposite of negative 4, we wind up with an answer of 4. But if we want to find the pOH, we then have to recall that the sum of the pH and the pOH always sum to be 14.00. So that means if we want the pOH, we're going to subtract the pH from each side. So we take 14.00 minus the pH, which in this case would be 14.00 minus 4. Is going to give us an answer of 10 for the pH. So again, the sum of the pH and the pOH will always sum to be 14. Will always sum to be 14. Any questions on that particular problem? Okay. Then, if we were to make a table like this, and let's say we want to compare the pH to the hydronium ion concentration. And now this refers back to the question we had here, this one right here. And we said that the correct answer was, at a pH of 3, it is 1,000 times more acidic. Now very often, I'll have students that'll answer 30 because they'll learn in biology, for example, that, well, every jump in pH unit is a factor of 10. And they go, well, 10 plus 10 plus 10 is going to give us 30. But we don't realize it's logarithmic, which means you have to take not 10 plus 10 plus 10, but 10 times 10 times 10 to get 1,000. And so when we look at the pH scale compared to the hydronium ion concentration, if we start at a pH of 7 and kind of work down, 7, 6, 5, 4, and 3, the hydronium ion concentrations respectively are 10 to the negative 7th molar, 10 to the negative 6th molar, 10 to the negative 5th molar, 10 to the negative 4th molar, and 10 to the negative 3rd molar. And so again, we can see that for each jump in pH unit, we have a factor of 10. This here is another factor of 10. This right here is another factor of 10. So again, each being a factor of 10, it winds up being 10 times 10 times 10, or 10 to the 3rd, which is the same as 1,000. So at a pH of 3, right here, pH of 3 is 1,000 times as acidic as a pH of 6. So again, pH of 3 is 1,000 times as acidic as a pH of 6. Now you say, well, what's the big deal on this? Well, one of them, first of all, is the fact that it's a logarithmic scale. Now, many of us don't understand what that is. Now, you, at this point now, hopefully you remember that part, but there are some other places out in the real world where the logarithmic scale is used. And one of the places it's used is when we talk about earthquakes. Earthquakes are measured on something called the, anybody know what that scale is called? The Richter scale. And the Richter scale is also a logarithmic quantity. And if you, now that's one where the values increase, they become stronger. So if you talk about a Richter scale 9 versus a Richter scale 8, a Richter scale 9 earthquake is 10 times as intense as a Richter scale 8, which is 10 times more than one of the Richter scale of 7. And so then if you compare a Richter scale 9 to Richter scale 7, the Richter scale 9 is going to be 100 times the intensity of a Richter scale 7. And so some of you now in semi-recent history may recall the earthquake in Japan here a few years back. They were debating between, well, is this a 9.1 or 9.2? And it was going back and forth. Well, you can see even why scientists argue about, is it 9.1 or 9.2? Because even just a small difference in the decimal corresponds to a big difference in magnitude in terms of those earthquakes. And how when you look at whatever, I think they finally established was a 9.2, compared to the one, let's see, there's one in Ecuador, I think, here about a week ago, right? And that was a Richter scale 7 point something. Okay, let's say it was 7.2. I don't recall hearing what that was. But again, that tells us that one in Japan that resulted in that tsunami was 100 times stronger than the one here that was in Ecuador. But now you look in Ecuador, you're probably going to see a whole lot more damage than there was in Japan if you actually looked at the shaking portion, simply because the construction and the engineering of the buildings is much better in Japan than it is in Ecuador. And so very often when you look at damage, it's not so much the intensity of the earthquake, but it's into how a lot of those buildings are designed and engineered. Sound intensity, when we talk about decibels, that's another one that's based on the logarithmic scale. But it used deci, so there every jump in 10 decibels is a factor of 10 in terms of sound intensity. So if you go from 80 decibels to 90 decibels, that's a factor of 10. From 90 decibels to 100 decibels, that's a factor of 10. So 100 decibels is about 100 times as loud as 80 decibels. So again, that's another place where the log scale is used. Now going back to this here, why does this matter? Well, one of the places where it matters, and what was talked a lot about when I was a student in your seat 30 years ago, what they talk about today is a little bit different. Back then we talked a whole lot about acid rain. When we talked about acid rain back at that time, and it's still a concern, acid rain is rain that is basically polluted. And it's either polluted with what we call sulfur trioxide or nitrogen oxides. And these subscripts are X and Y, and that's because there's so many different nitrogen oxides that can form. But what happens in the case of the sulfur trioxide, and we'll just look at this as an example, what happens here is that we burn coal that contains sulfur. And we burn coal containing sulfur, what will happen is that the sulfur will react with the oxygen to form sulfur dioxide. And then the sulfur dioxide will react with oxygen to form sulfur trioxide. Balance is something like this. Well, then the next key is what's critical. What happens next then is that the water will react with the sulfur trioxide to yield H2SO4, which we call sulfuric acid. And if we go back to where we started today, what we see here is that sulfuric acid is one of those acids that's classified as a strong acid. And that's one of the problems with acid rain. In fact, acid rain, at one point in time, the pH can get as low as 3. pH can be actually as low as 2. But let's say we say pH can be as low as 3. And then we compare that to natural rain. Natural unpolluted rain, you might think, well, natural unpolluted rain is neutral. Well, actually, natural unpolluted rain actually has a pH of about 6. And the reason why it's still acidic is because everybody in here is giving something off. When we exhale, all of us are giving off carbon dioxide, as is any other animal that's out there, is exhaling carbon dioxide. What happens is that the water will combine with that carbon dioxide to yield H2CO3, which we saw earlier today is classified as a weak acid. So see, naturally we should have a weak acid that's falling, and nature evolved intended to deal with that pH. Things did not evolve to deal with pHs of 3 and 4 or whatever else. So when we look at the oceans then are very slowly acidifying. And that's where we talk about it today. You don't hear about acid rain, but where you'll hear scientists talking about this big concern is that the pH of the oceans is gradually changing. And it's gone from something like 8.2 to 7.9. I don't remember the exact values. It's only 0.3 pH units or 0.4 pH units, whatever it is. But remember now that each jump in pH unit represents a factor of 10. So we talk about now these huge oceans which cover the entire Earth changing by a few pH units over a period of like about 40 or 50 years. That's then where we really, really need to be concerned, because if that trend continues, there's a whole lot of things out in the ocean that are not going to be able to survive that. So that's, I guess, if I were to say, why should we care about this? It's that eventually, if you don't have to deal with it, I don't have to deal with it, eventually the people that we make that come after us are going to be the ones that are going to have to deal with it. So here's what we're going to do the rest of the hour today. We're going to do some pH calculations, and so we need our calculators out. And on your calculators, we need to find these buttons. And those buttons are the log button. So find the log button. Then you need to find the sign changing button, which is either the negative sign in parentheses, or if you have a Casio or Sharp, you might have a +/- key. And then you need to find the EE button, which is on the TIs. If you have a Casio or Sharp, you have an EXP button. You might have one that says ×10 raised to some power button. So you need to find these 3 buttons. So this one of these, and one of these. And remember, if you have a TI-82 or 83 calculator, the EE is above the comma. So you have to do a second function to access the EE. So then to calculate the pH, let's say we'd like to calculate the pH of a solution. Using the calculators, calculate the pH of a solution where the hydronium ion concentration is equal to 5.6 times 10 to the -5th molar. Well, then to calculate the pH, we remember that the formula is the pH is equal to the negative log of the hydronium ion concentration. We're then going to substitute into the hydronium ion concentration a value of 5.6 times 10 to the -5th. We want to calculate that answer. So now, if you have a TI graphing calculator, here's the way the key sequence is going to be put in. And you're going to just put them in from left to right. First thing you're going to do is hit your sign changing key. Then you're going to hit your log key. That's going to put in a left parentheses for you. Then you're going to enter in 5.6. Then you're going to hit the EE button, and then your sign changing button, and 5. You'll then put in the right parentheses, and then you are going to enter. And if you have an older model calculator, and by older I don't know what older necessarily is, maybe older single line Casio or Sharp, yours is going to go in like this, 5.6. You're going to hit the EXP button, then your sign changing button, and then you'll hit the log key, and then your sign changing button again. And you get the answer. So run through that. Negative log 5.6 E negative 5. And once I do that, you should be getting 4.25 something. Make sure that you get 4.25 something. You can get that on your calculator. Okay, 4.25 is this pH. Now, next thing we'll need to do is talk about significant figures. And I have the correct number of significant figures shown for this one. And we'll talk about why we put it out to 2 decimal points here with the next example. So, for this one here, in the 5.6, which digit is the uncertain digit?
6.
It's the 6 there. Remember, it's the last digit. So, then what we're going to do is change that digit. Let's say we want to find the pH of a solution that has a hydronium ion concentration. I'm going to change it to 5.7 times 10 to the negative 5th molar. So we go back and we change that. And we see the way that this changes now is the answer is 4.24. Now that means that changing this digit right here, change this digit here. And the reason why that's important is because if we go back to, and this is like probably day 2 in here, we had a definition for significant figures, and we said that significant figures are all of the certain digits plus one uncertain digit, and this here is that uncertain digit that we're getting from that calculation. So let's do another example, and make sure you can come up with these now on your calculators. Let's say that the hydronium ion concentration, I'm going to keep the 5.7 there, but now I'm going to change the number to 10 to the negative 4th molar. So now I'm changing this number up here. Let's see what that does to the pH. And we come up with 3.24. So you see now, what's happening is that that number in front of the decimal on the pH changes when the exponent changes. So this digit right here is determined by the exponent, and the digits after the decimal are determined by the values in front of the power of 10. So again, these here determine what comes after the decimal, the pH. The exponents here determine the values that come in front of the decimal. So what that then means for significant figures on pHs is this. If your hydronium ion concentration has 2 decimal places, then your pH, not 2 decimal places, 2 significant figures, then your pH is going to have 2 decimal places. So again, if your hydronium ion concentration has 2 significant figures, then your pH is going to have 2 decimal places. The number of decimal places on the pH is equal to the number of significant figures in this measurement. Which then is going to take us down to, I believe, our last two Socrative app questions of the semester. And the next one here is a variation on the same theme. Now we're looking at 5.7 times 10 to the negative 6th molar. 4, 3, 2, 1. And we should have 5.24. And to the person who put in pH on here, we'll emphasize, if I didn't already, that pHs are dimensionless, which means there are no units. So we say the pH is, and there's no units that come after that pH. So in this case here, we simply say the pH is 5.24. And again, we see by changing this power to negative 6 here, we simply change the digit in front of the decimal. The digits after the decimal here remain the same. All right, that's significant figures. Last page here. We're going to be responsible in this course for calculating the pH of two types of solutions. They are the pH of a strong acid and the pH of a strong base. And when we calculate the pH of each one of these, notice again we're talking about strong acids and strong bases. We are not going to be responsible for calculating pHs of weak acids and weak bases in here, because the level of mathematics required for that would require about another, I don't know, a week or two of work, because the mathematics are much more complex. The mathematics for strong acids and strong bases is very simple and straightforward. So in order to calculate the pH of a strong acid, here's what we need to know. The hydronium ion concentration is equal to the concentration of the acid. Remember that the square brackets stand for molarity. So if I know the molarity of the acid, we also know the hydronium ion concentration. In a strong base, it's a little more involved. In a strong base, the concentration of hydroxide ions is equal to the concentration of the base times the number of hydroxide ions in the formula. So then what we're going to do is this. We're going to do three calculations to show these how they're used. First one we're going to do is we're going to calculate the pH of 0.10 molar hydrochloric acid. If we had to classify HCl, HCl would be classified as a strong acid. And so when you're doing this on your exam next week or on your homework, you would refer back to these and you would see, oh yeah, HCl here is one of the strong acids. So since it is a strong acid, what that means is that the hydronium ion concentration in this case is equal to how much? 0.10 molar. It's going to be the same as the concentration of the acid. And now that we know this, then we can calculate the pH of this solution, because the pH is equal to the negative logarithm of the hydronium ion concentration, which means we're going to substitute in 0.10. If we take the logarithm of 0.10, and actually you can run this through your calculators, you're going to wind up with an answer of 1. But now we need to think about significant figures. How many significant figures does this measurement have?
2.
It has 2, which means our pH should have 2 decimal places. We'd write it as 1.00. And that is the answer for the first one. Then we ask ourselves, does this pH make sense? And And we come back to our pHs, which tell us that on the pH scale, somewhere here, I think we put it right here, there we go, that it is acidic if its pH is less than 7. That's a really low pH, which it should be for a strong acid. Then we go to the next one. And we say, let's calculate the pH of 0.10 molar sodium hydroxide. Well, sodium hydroxide now we would classify as a strong base because it is a group 1A hydroxide found right here. Sodium hydroxide is going to be a strong base. So, if it's a strong base, then the first thing we can do, now we want to calculate the pH, but we can't find the pH first because we don't know the concentration of hydronium ions. We do, however, are able to first find the concentration of the hydroxide ions. And the concentration of hydroxide ions are found like this. Tells us we're going to take the concentration of the base and multiply it by the number of hydroxide ions in the formula. Well, the concentration of the base is 0.10 molar. And how many hydroxide ions are in this formula?
1.
Just 1. So we're going to take 0.10, multiply it by 1, and we get 0.10 molar. Well, now we have the hydroxide ion concentration, which means we still can't find the pH, but we can find the pOH. And we find the pOH by taking the negative logarithm of the hydroxide ion concentration, which means we're going to take the negative logarithm of 0.10, and we wind up the value of 1.00, just like we did when we found the pH up above. Remember now, this is the pOH. We want to find the pH. So what are we going to do next?
14.
Right, we need to remember that number 14. And that's because the sum of the pH and the pOH sum to be 14.00. Well, if we subtract the pOH from each side, we find out that the pH is equal to the 14.00 minus the pOH. And then we can substitute in the values properly. We'll take 14.00 minus 1.00, and we wind up with an answer of 13.00 as the pH. And then once again, when we get this answer, we ask ourselves, does this answer make sense? When we come back to our pH scale, and if we have a high pH that is greater than 7, that tells us that this is going to be a base. And a strong base should have a high pH. And the last one is on the Socrative app as well. And it is this one right here. We want to know, what is the pH of 0.0023 molar barium hydroxide? Now in this one here, this has how many hydroxide ions in the formula? There's 2. There's 2. So remember then that you need to first find the hydroxide ion concentration, which is equal to the concentration of the base times the number of hydroxide ions in the formula. 11.66 is correct with the correct number of significant figures. Those that have 2.34, what did they forget to do?
Subtract 14.
Subtract from 14, right. So the 2.34 was the pOH. We wanted the pH.